Okay.
Our next speaker is Leonard Susskind from Stanford.
Thank you. I once gave a seminar at Harvard. a long time ago. And after about 10 or 15 minutes, Sidney Coleman jumped up and he said, "Oh, what you're doing is beautiful. I love it. I've never seen it before, but let me try to finish the seminar for you. Sit down." And I did. And he finished the seminar beautifully. So if you're as good as Sidney Coleman, I invite you to finish my seminar for me. But otherwise, please, just let me finish. This is a true story. Well, it's as true as any of my stories. But okay. A thing which I've learned through experience is that when you keep thinking the same thoughts over and over and over again, and in the process refine them and refine them and refine them, using the same logic over and over and over, you often just get deeper and deeper and deeper into your confusion. And the more precise you try to make those arguments, the more you get confused. The reason is you don't want to take wrong arguments and be too precise with them. Just a mistake. Better question your assumptions. Better question your assumptions, even the ones you think are most solid. When you get into these really, really paradoxical situations, and assume that you're making some mistake. If I had to guess what mistake is being made by the firewall people, and there is one, I'm sure, it is assuming that the states with firewalls, or perhaps the states without firewalls, it doesn't matter, form a linear subspace. In quantum mechanics, we usually say states that have a certain property form a linear subspace. An observable has a certain value if there's a firewall operator. If a firewall operator is 0 or 1, depending on whether there's a firewall, normal logic would say that the states which have a firewall are a linear subspace. And if you can prove that in a given basis all states have property X, that's enough to prove that in all states, not just those basis states, you have property X. But that's making the assumption that a set of states with a certain property are a linear subspace. It may not be, and I'm going to argue today a little bit. You may not notice where this argument comes, but it'll come. That the set of states which have a firewall are not a linear subspace. You tell me 5 minutes, that's all I have?
I want to ask a question.
Yes? Yes.
Thank you.
Go ahead.
I'm just, since you're really pointing this out as so central, it's not clear to me where that assumption has been made.
When you say that all unentangled states have a firewall, and from that conclude that all states have a firewall.
But I didn't.
I know. I wasn't blaming you, but something like that is something along those lines.
No, I said that that's enough to violate the equivalence principle. So I think this point is important because you can disagree with that conclusion, but that's a different argument. And then similarly with the donkey maps, the assumption is very much not that firewalls necessarily form a complete that they have linear properties, and we're engaging with that on that.
No, absolutely not. No, I'm going to start my seminar now, so let's begin. I'm going to be talking about the relation between Einstein-Rosen bridges and entanglement, at least a little bit, and some other issues, and try to tell you what I find most confusing about it. I am going to try to tell you what I find most confusing about it, and I think probably Juan shares some of my confusions, but we'll find out from him. The origin of this study, I think, originated because both of us were concerned about the fact that in some sense the idealized double of the eternal black hole is a counterexample to the statement that purity, maximal entanglement with a distant system, and no drama can't be consistent. It's a counterexample to saying they can't be consistent. And so we decided to try to debug exactly what the dilemma that AMPS had stated, or what it was, and how it is that this highly entangled system nevertheless seems to be able to have purity and no drama at the same time. So let me just remind you about that system. I'm not going to spend a lot of time at it. Whoops. We're talking about the ADS eternal black hole that Juan has studied over the years. Consists of two quantum field theories, one on the left, one on the right. That's the holographic dual of the system, two quantum field theories. And if you're interested in the thermal field idealized double state, which I think we know, although I think it still could be argued, I think, but I think most of us agree that this state has no firewalls. So let's analyze it and see what's going on. All right, the thermal field double, just to remind you, I think most of you know it, thermal field double state is just the sum over the energy levels of either side, e to the minus beta over 2, e entangled state, highly entangled state, e left, e right. And that's the setup. It has a symmetry on the time translation invariance, where time translation invariance means this funny kind of time translation invariance where you push up on one side, push down on the other side. But that's sufficient to say that if there's no firewall at time t equals 0, then there will never be a firewall, because by symmetry you can get up into the corner here and discover that there would be no firewall for Bob jumping in over here by applying the symmetry operation, which lowers you here and raises you on the right-hand side. Okay, the thermal field double state can be thought of in at least three ways. The first way as a trick for calculating correlation functions in a thermodynamic system, non-equal time correlation functions. I'm not interested in that sense. The second way you can think of it is as a pair of black holes infinitely distant from each other, or you can say on two completely separate non-interacting sheets, two separate black holes in two completely non-interacting worlds where the two black holes are maximally entangled. Maximally entangled I take to mean this kind of state here. All right, so if you have two black holes in otherwise non-interacting world, in fact, not otherwise, in a completely non-interacting world, but you entangle them in this form here, the statement is that they form a Einstein-Rosen bridge between them. Form, I don't know if that's the right word. They have an Einstein-Rosen bridge between them. And if so, at least under in certain circumstances, you come to the very interesting fact that these two non-interacting worlds nevertheless can communicate, not communicate outside to outside, but somebody falling in here can meet somebody here. And that's a rather curious fact, that even though they are completely disconnected worlds, if you manage to make a pair of black holes that have this kind of entanglement, it seems that two people could jump into the same one into the left black hole, one into the right black hole, and meet at the center if they jump in early enough. Curious. The third interpretation is two black holes in the same space-time, but very far from each other. So a black hole over here and another black hole over here. But again, with horizons identified corresponding again to the same kind of maximal entanglement. Same kind of maximal entanglement. Nobody has ever proved that such correlated black holes have Einstein bridges between them, but I'll take it as a given. And we'll talk about it a little bit. We'll talk about what it means. Okay, first question that should occur to you is how the devil do you make such things? How do you create such things which have this kind of entanglement for very, very distant black holes like this? What's the formation mechanism? Okay, so let me begin with one example which is known. This is an example. I can't remember who the authors were. I know Andy and were you involved? Yeah. Garfinkel, right. Studying pair creation of near extremal black holes in an electric field. What they found was that pair creation can happen, number one. Number two, the coefficient in front of it, the density of states coefficient, was consistent with saying that they were maximally entangled. In other words, there was a factor of e to the entropy of one of the black holes, which corresponds to exactly this kind of situation over here, maximal entanglement between the two of them. And finally, their geometry, their instanton, indeed did contain an Einstein-Rosen bridge between the black holes. They were accelerating outward, accelerating away from each other, so indeed you can separate them and the bridge just grows rapidly. So it is possible to create this kind of situation. All right, let me talk for a few minutes about parallels between entanglement between ER and EPR. Just very briefly, I'm not going to go into it in great detail. Both entanglement and Einstein-Rosen bridges have the property that there's some kind of connectivity, but you can't send information through it. You can't send information from one side to the other side for reasons that I won't. In both cases, you probably know the reasons. You can't send information, even though there is a kind of, in this case, geometric non-locality, in the other case, just plain entanglement. Second, you can't create, in either case, you can't create either a bridge between two black holes, or a bridge between two systems, or entanglement between two distant systems by local operations. This is the quantum information people say you can't create entanglement by something called LOCC. I don't think the CC is important for us. LO means local operations. And local operations means separate operations which don't talk to each other. Could be unitary transformations, for example, on the left or on the right. You cannot create entanglement that way. And I also believe that you cannot create an Einstein-Rosen bridge between two black holes that didn't originally have one. Not by doing operations. Well, I should say, I take that back. You can do it, but not by local operations which don't talk to each other. So let's talk about the various ways of creating two distant entangled black holes, or even just taking two black holes which don't have bridges between them and create a bridge between them. The simplest way would be to make a whole bunch of, this is my picture for two little black holes created nearby, perhaps by the Schwinger creation mechanism. Here's one, and it's entangled, well, it is entangled with this one over here, but for the moment it just has a bridge. You create sets of pairs like this, and then you just let them fly out and take half of them, put them into this black hole, take half of them and put them into this black hole. These bridges will sort of grow together. They'll, coalesce is the right word. They'll coalesce and form some kind of bridge between here and here. I think under appropriate some circumstances, you can make that bridge be a classical, pretty classical geometry.
How do you know you get a rate of the bridge?
I don't know. I'm guessing. I
suspect they might not.
But you may suspect they may not. One suspects they do. And Sidney, who is dead, is almost sure they do. That was not a question, incidentally. That was not a question. Is this a question? Are you asking a question or are you making a statement?
I suspect it might not either.
That's another non-question. Okay. You should. All right. Also, and Okay, yes. Okay. The other thing that you can do to create entanglement between the two black holes is create entangled bell pairs. I always draw a bell pair by putting a line between the two particles. Okay? So what I will mean by two particles or two qubits with a line between them is a bell pair. A bell pair means a maximally entangled, and it doesn't even have to be maximally entangled. You're using your entangled systems as a resource, stretch them apart the same way, drop them into the black holes, and you'll create entanglement between them. It is a conjecture. There's no theorem, because I don't even think there's a basis for being able, we don't know enough to even formulate the theorem. But the conjecture is that if you create enough entanglement this way, you will create an Einstein-Rosen bridge between the two black holes. Okay? I think...
The question is, do you really think just the amount of entanglement is important, not the precise form?
Let me just... The question is whether it's a smooth geometric solution of Einstein's equations and so forth. That's part of my message. We have to learn to understand under what circumstances we create geometry and in what circumstances we just create mess.
If I could respond to that, and since this seems to be Jeopardy in the form of a question, isn't it true that after making a not necessarily exact state, you can then act with unitary operators which are local to make it be the right state?
Yeah, thank you. Thank you. I like that question. At least under some circumstances. Right. You can operate with local operations to make it...
Another question. Given your introduction and your use of the term amount of entanglement, are you proposing that the existence of a wormhole is not characterized by a linear operator?
Yeah. No, I am saying any given wormhole is associated with some particular state. But the overall question, is there any kind of wormhole between them, including ones that may not even have nice geometry? That is just the question of whether there's entanglement between them, and that is not given by a linear operator. The manifold of states, for example, which are maximally entangled, is not a subspace, not a linear subspace. So, right. Okay, so the hypothesis, the conjecture, is this conjecture which we write with which Juan wrote with a clever acronym ER equals EPR. When I saw that, I just knew it had to be right. How could that be wrong? How could we waste such a thing?
Does it mean that Podolsky is one or that
That's the way I used to write it. When I would write one messages, I would say using P equals 1. Okay. Now, clearly, this does not mean that any kind of maximal entanglement between some qubits, well, I don't have to separate them, doesn't matter where they are in space, that any kind of entanglement between qubits forms classical geometry. For example, just having things in the form of bell pairs, this bell pair unentangled with this bell pair, unentangled with this bell pair. If we want to think of this as a very highly quantum mechanical bridge, which I don't think means very much, the whole thing does not form any kind of classical geometry. It just forms a whole bunch of these super quantum mechanical things. All right, now supposing we come along, let's call this the left-hand side, let's call it Alice's share, the right-hand side Bob's share, and now come along with a unitary scrambling operator that only scrambles the right-hand side. A random unitary that scrambles, that acts on, I guess it's Alice's share, I can't remember which was which acts on Alice's share, and that creates an entangled state where everybody is entangled with everybody else. Everybody's entangled with everybody else to a very, very high entanglement entropy. Maximal entanglement entropy, very close. And it's pretty clear that that has to make some kind of, to the extent that this hypothesis is true, it creates something which is connected in a way which you can't separate off any subsystem of them. So I would tend to draw this, again, this is in the spirit of free flying for a while until we get some ideas and get, let's think of this then as some kind of structure. This is the wormhole, the real space. Let me draw it this way. Here's space. Does it? Yeah, look. Oh, yes, you're right. So these are our qubits out here, and somewhere in the Einstein-Rosen bridge associated with them is more connected. It must be more connected, and to the extent that it does form a geometry, you might expect that the area of that geometry is proportional, or the area when you cut through it in any particular way measures the entanglement entropy of the set that you've cut into, the way you've cut it into halves. Say it again. Yeah, but the entropy can't evolve unless they're doing something new. Yeah.
So I was wondering if we have a picture where the background space-time itself is there in some sense because of entanglement between freedom, and then I add. So if I then have particles and I entangle the particles in the space-time, is it obvious that the net entanglement increases?
I didn't get it.
Well, so I guess if we're entangling to some particles that were in a pre-existing space-time.
Yes. In here.
I guess I have this picture with some pre-existing entanglement that is responsible for the space-time being there.
Yeah, that's a different. Yeah. Okay.
So if I add the entanglement in the space-time picture, does that always increase the net entanglement?
My abilities to multitask have gone to zero with age. And I really find it hard to think about what I'm going to say and what somebody else is saying at the same time. So I'm serious. I'm serious. I do have trouble with it these days. I always had trouble with it. I prefer to get those kind of questions. Let's wait for them till the questions. That's a serious question. Let's wait. Yeah, let's see if we make it sharper. All right. So let me come back to here for a minute. Here for a minute, it's quite clear that there is an Einstein-Rosen bridge between the left side and the right side. So maybe, not maybe, I think we really think, that the presence of this Einstein-Rosen bridge is deeply connected with the resolution of the paradox of why this state can have smooth horizons even though it's maximally entangled. Good. All right, so that sort of sets us up. Next step, this was just a cloud of qubits that was very, very highly entangled, and it created some kind of structure. And as Don correctly points out, it's not clear in the least that any random thing like this looks anything like classical Einstein geometry, and I would agree with that completely. So, now, yeah.
If you did have a nice classical wormhole, what is the test by which I would know that there's a wormhole exhibiting here and there?
You and your friend jump in. First, you have to do a complicated quantum computation on it to readjust some phases, and then you jump in, and your friend jumps in from the other side, and if you meet at the center, you know there was a wormhole.
Okay, so that means it's traversable.
No. It does not mean that it's traversable. Are you sure you want to ask?
So if that's the test, people can jump in and be in the middle. you have a sharp way of showing?
Why don't you wait for the question period, for God's sakes? That sounds like a very serious question. Why not wait until I'm... Good. Thank you. All right. So here's the basic hypothesis. The basic hypothesis is when a black hole evaporates, particles go out, and they are, of course, entangled with a black hole. Eventually, you have a cloud of a large number of particles, maybe even more particles than there were entropy in the black hole to begin with. But the assumption is that because the black hole remains at every stage maximally entangled, well, it depends on who's bigger, but there's an entanglement between the black hole and the Hawking radiation that indeed these must be connected. Let me try to draw it. Here's the Hawking radiation out here, that these must be connected by some kind of bridge. Now, we certainly expect the bridge on the Hawking radiation side to look nothing like a smooth classical geometry. The question, now this is a question, this is not something that either Juan or I can prove at the moment. The question is whether the bridge at the black hole end stays smooth. That's the question. How to answer it, I don't think we know. I don't know. Do you know? Oh, you're working on it. That's right. You're working on it, and by the afternoon, hopefully, we'll know. But I don't know how to think about it, but it's a sort of framework for thinking. It's a framework for thinking. And this object has a name. It's called an octopus. My wife says it looks more like a squid. So, cuttlefish, right. All right, now let me abandon this line of thought for a moment and come to another line of thought, which is more based on very little that I know about quantum information theory. I want to set up a kind of model for thinking again, a kind of model for thinking about the problem we're facing. And here's the setup. Let's start with a message. We have a message, and we want to encode the message, burying it deeply in some very highly entangled thing. This is probably connected with fault tolerant, blah, blah, blah. John can tell me if it is, but here's what we want to do. I have a couple of qubits, and I'm now going to draw them as lines. The arrow doesn't mean anything. I just want you to point to the right. This is a 3-qubit message. It's a 3-qubit message, and I'm now going to do something, and I will tell you what it is in a moment, through a code, to bury it in a large number, but bury it faithfully in a large number of qubits. I'm going to call the message A. I'm going to call the thing that I bury it in H. This is the system in which it's buried. I'll call this the code, but I'm going to do one more thing before I send this message in. I'm going to keep a record of it. Now, you can't keep a record of a quantum message by cloning it. But what you can do is you can maximally entangle it with another set of qubits. The information people like to do this, what is it called, a control? Reference system. Yeah, a reference system which is maximally entangled with these qubits A. After they go through here, the reference system, Joe, would you care to guess what the name of this one is? B. Maybe B till the star dagger. I don't know. B. All right. So we have encoded a certain message, not a certain message. In fact, what we've done here is encoded all possible messages, but entangled with all possible messages. A small number of qubits buried in a big number of qubits. What's the correspondence with black holes? Just for this model. This is not to be taken too seriously. All right. B is, of course, the zone. Are we ever going to agree about what to call? Well, everybody calls B the zone. Is that right? Yeah. Good. So B is the zone. B is the zone. It is maximally entangled with the message. The message is the interior. But that message has really been encoded, or I don't know what to say, encrypted, I don't know what to say, in this stretched horizon here. And that's H. this is the information model I'd like you to think about. Okay. First question, how do you build such a thing? How do you actually do this? And this is easy to do. If I have a message coming in here, my code can just consist of taking 3 qubits, and this is B over here, H will be over here, and maximally entangling them into bell pairs, and a whole bunch of additional ones. I don't know if these are called ancilla or not. Are these called ancilla? I don't know what they are. They're just, and initialize the state of the rest of them. The rest of them is whatever it takes to build up H here. Initialize the rest of them. It could be in a particular state all down, but it could or all 0. But it could also be some other state. What we do here is part of the initial state of the black hole. Part of the initial state of the black hole, exactly how we initialize this. Then we take this system here and run it through a random unitary to scramble it. After that's done, we now have B maximally entangled in H in a very, very complicated scrambled way. And I don't know how to draw that. I mean, I don't know how to draw it in any decent way, but nevertheless, let me just, well, a whole bunch of qubits here. And everybody is entangled in some monstrous scrambled state. Maximally entangled. Everybody is maximally entangled in the usual sense of a highly scrambled state. The message is in here. It's faithfully recorded. And in that sense, the interior of the black hole is encoded in the stretched horizon, if you like. Okay. Now.
A is smaller than H and A is, I don't know, like 3
That's right. Yes, it's a theorem that the size of A is the same as the size of B because it's maximally entangled with it equally. That's a joke. And I assume that B is much smaller than H. All right. Typically, it's likely in string theory to be something like G squared times, but it's not important. Yes, I do assume that H is the much bigger system.
But again, it's not one interior, it's all possible interiors.
Yeah. That's in some. Yeah, so that's right. Right. Okay, now another piece of lingo. Another piece of lingo is that the state here, psi, can of course be written as a sum over any basis of states of B, so let's call that I sub B, times an orthonormal family phi sub I of H, where phi sub I are an orthonormal family of a subspace which is significantly, which is no bigger than B. Okay. Phi sub I here, or better yet, the space spanned by the phi sub i's is called the code subspace. Did I get that right, John? Is it called? I think it's called the code subspace. Good. This is the code subspace, but it is also the space of states of the interior of the black hole. Think of it as the code subspace here, as the space of states of the, after all, what this code subspace is doing is it's just encoding B in a maximally entangled subspace here, but the thing that B is entangled with is supposed to be A. So the code subspace becomes the Hilbert space, if you like, of the interior of the black hole. Okay. What else to say about codes? The other thing is, of course, that the A operators act in the code space. The A operators are operators, or the operators of the subsystem A, the original subsystem A, become operators in the code subspace. The code subspace is no bigger than the space of the black holes, so any operator has to be defined in a way that doesn't have any more states than A. But it's quite clear that the A's are very, very scrambled from the point of view of the original defining qubits. let's say from the point of view of these originally defined qubits, the nature of A is to be impossibly complicatedly scrambled in this message here. Very difficult to extract unless you know the code in detail. And even then, it's hard. All right, I will also define the A's. This is a matter of definition. I will define them to annihilate the subspace orthogonal, the orthogonal complement of the code subspace. That's just a matter of convenience and definition so that I have a definite definition. What is true is that, where was my initialization? My initialization was to take a small number of qubits, maximally entangle it with B, and then put all of the others in some definite initialized state. The code subspace and the operators A, as they act on H, are very, very sensitive to the initial state. The whole code subspace itself is incredibly sensitive, really incredibly sensitive when you have a large number of qubits here. You just change the initialization by 1 qubit, and you entirely change the subspace that the, in other words, you entirely change the way A is encoded in the defining qubits of H. So that's something to keep in mind, that if this kind of model is right, then the encoding of the ordinary smooth degrees of freedom behind the horizon is likely to be just wildly complicated, wildly complex. Okay. How am I doing for time?
20 minutes.
Okay. We'll just go where we go and just end it when it's time to end. All right, now let's talk about Hawking radiation. Hawking radiation induces errors. Incidentally, a lot of this is quite similar to what the Verlindes wrote in many ways, and you can read quite a lot of similar things in what Herman and Eric wrote, and there's some differences, not yet, but not important differences. Okay, so now let's erase some qubits. Erase them because they've evaporated. Now, of course, there will also be some which will be evaporated from B also, but let's not worry about that. Qubits are erased by evaporation. They're no longer there. Is the message still encoded in H? Yes, up to the point where half the qubits have been evaporated or missing. That's, of course, Page's argument, but it's also something that the quantum information people know as, in terms of quantum error correction, you could error correct basically up to about if a number of errors, which is half the number of qubits that you have, if you know where the errors lie. If you don't know where the errors lie, it's n over 4. You can erase more than that and still recover the message? Yeah. If you don't, I think the rule is if you don't know where the errors are in a code, then you can n over 4. I understand the n over 2 very well. I have no idea how the n over 4 is proved. So there's a kind of threshold for loss of. Yeah.
So do you mean that the bits, so to speak, in H are transported out into outgoing radiation?
That's what I mean.
So, okay.
Yeah,
so
right.
That's not really the Hawking process. That's something else. That's not really
the Hawking process. Yeah.
The Hawking process builds more entanglement between inside and outside.
Well, it does. No, it doesn't. It transfers the entanglement
Unitary.
that's there to. That's right. So that's what I was about to say. You haven't really lost the message. Clearly, you haven't really lost the message. The message is now just in the entanglement with B and H and the whole thing with the rest of the Hawking radiation. You haven't lost the message. In that sense, A is still intact in this model. You've just transferred it out to the Hawking radiation. Okay? And this, of course, brings us to A equals RB. Before we introduced radiation, I would have said A is equal to HB, meaning to say A is equal to the subspace of H, which is entangled with B. Now, I'm inclined to write A equals RB, but I don't think that's exactly right. The right thing is really R plus HB. Meaning to say that part of the code is still, part of the code may still be in H. On the other hand, it's probably enough, if a large enough number of qubits are radiated out here, that the message can be pretty much recovered by looking at the qubits in R. So call that A equals RB. Let me draw another picture of this. Here's the stretched horizon. Here's the radiation out here. The hypothesis is that there's an Einstein-Rosen bridge connecting them. The Einstein-Rosen bridge is nothing more than the entanglement, but under certain circumstances, entanglement yields classical geometry. So there's an Einstein-Rosen bridge, but it's a hypothesis or a speculation that the Einstein-Rosen bridge is such that it has smooth geometry at this end. And I can no nothing other than idle speculation. I have a lot to say about what I hope, very little to say about what I know. Good. Okay, now let's talk about what happens if somebody comes along and interacts with one of these qubits. Somebody comes along and interacts with one of these qubits. They've interacted with R. Does it do anything to the message? Okay. It would do something to the message if you insisted that the message, in particular, if this qubit becomes entangled with the thing that measured it, with the pointer that measured it over here, then you would have disrupted R sub B over here. But really, another way to think about it is all that happened is the octopus has grown a little bit. And what's really happened is the message got transferred not into just R plus H sub B, but R sub H plus everything else. Everything else, EE. And it's still there. The message, I mean, if you believe in purity, then it follows from purity that that message is not destroyed. It's still there, but it's now found in here. And what you might say is that the code has had to be readjusted for this interaction here. That's the way Raphael likes to call it, readjusting. You call it readjusting the code. Yeah, so that's readjusting the code. And the message hasn't been lost. Nothing's happened to it. So no problems. But if you read the paper that Juan and I wrote, and I'll let you read it in order to solve the first amps paradox, something else was necessary. It was necessary if somebody comes along and actually measures RB, enough quanta in here to reconstruct the thing which is entangled with B. And that's a lot of quanta. It's at least S over 2. If somebody comes in here and somehow runs S over 2 of these through an appropriate quantum computer, which our friends Harlow and Hayden say is impossible to do in less than a certain amount of time, but I'm gonna pretend I can do it faster. Incidentally, why do I pretend that? Because those are the rules of the game that Joe and Don and I'm sorry, I'm blanking. Alice can do any measurement. Alice can do any measurement. So Alice comes along and measures more than n over 2 of them. That must send a signal into A. It must send a signal into A, because if A is equal to RB, you've effectively measured A, and measuring A is going to disrupt. If you measure the creation operator for A, you'll disrupt the annihilation operator, and so forth. So, and I think that must be right, that making a measurement over here of a complicated enough kind basically inducing some complicated error, must be able to send a message to back into the interior of the black hole. So we now have a paradox, or a puzzle, operating on any individual easy mode. Let's call these the easy modes, the easy things to measure. Operating on any one of them, or even up to n over 2 of them, does nothing to the interior of the black hole. Operating on enough of them somehow sends a message back, but enough of them is simply a function. R sub b is a function of the easy modes. How is it that measuring that many of them could do something that measuring no one of them could do even a little bit?
You also have a question. When you originally, you said that this is perhaps very quantum, very non-classical, perhaps very much different from the sun.
Yeah.
And also this word to be very long.
Yeah.
You're saying it must have the key property of Einstein rows and you can send a message back to get near the horizon on the other side.
That is what we say. Now, the kind of measurement that has to be done here is not simple. It involves collecting the qubits. It involves running them through a quantum computer, readjusting the phases to make them maximally entangled, and which very likely is totally impossible. But but the quantum operation is shortening the bridge, and then you throw the particle in. In other words, the claim is that any measurement which is complicated enough to decode RB has all of those ingredients in it. Okay? Now, it seems to me that has to be the case.
Rather than doing the big complicated thing all at once, you can just break it up into little things and do one after the other. And what you're going to say is that each little thing that you do does nothing, but then somehow after you do a whole bunch of them, then it does something.
Something like that. Something like that. Right.
And this is the thing that
Right. No. This, I think, is where the trouble is. This is where the trouble is. So, not understanding it, we're inclined to come back to ADS-CFT and understand if we can see what's going on there. Come back to the eternal black hole. How much time do I have? Oh, okay. I think we can do it. Okay. So, translated into ADS-CFT language, the thing which is entangled with B over here is a mode down in the left-hand corner, sort of diametrically opposed.
Now the question is sort of different from the argument that I gave yesterday with this network, which is just at the level of defining the difference between the computational and the logical bits. When you treat something as a computational bit, you're invoking some sort of locality.
I imagine yes. I believe so. Yes, I would say so.
And so I could use the logical basis, right?
What does the logical basis mean?
I mean, the basis in which basic elements are particular.
Where the entanglement was simple? Yeah. Right. That's a very, very complicated thing from the point of view of the.
But you are saying that there's some fundamental significance to the locality of these qubits.
Yep. Right. So that's why I want to return to ADS-CFT and see if we can see what's going on. So I think we have a bit of understanding, certainly not a complete understanding, but some pieces. Okay. Back to ADS-CFT. First thing is that the thing which is entangled, this is B, outside the horizon. Oh, sorry, let me just set up the game. The game is to think of the right side here as the black hole, right for black hole, and left for radiation. Oh boy, R for right, left for radiation, yuck. The right side here is Bob's black hole. The left-hand side is the replacement for the radiation. Bob's black hole is maximally entangled with the radiation, and now we want to do operations on the radiation and understand under what circumstances they send a signal to A. Under what circumstances do they send the signal to A? All right, so it's more or less clear that if you make a perturbation, let's call it a Schenker-Stanford perturbation over here, that this is A. Over here, it'll send a message to A. Okay. Let's give this a name. The operator over here, I'll call A prime. And in some approximate sense, I stress approximate because I know extremely well that this is not exact. But in some approximate sense, let's identify A with A prime. This is a kind of A equals A prime theory. Meaning to say that if you evolve A prime upward to the right, it becomes A. Okay, so in particular, if you perturb A prime over here, measure it or anything else, you expect the particle to appear over here. Okay, but I want to think about operators at equal time, more or less equal time to A and B over here. And so what I do is I run this operator upward using the equations of motion. What I'm actually doing is rewriting A prime in terms of operators at a later time. Let's call that A double prime. I'm sorry for the notation. I just ran out of letters. So let's call that A double prime. What is it? A double prime is by definition U dagger. I never remember which side has the dagger. A prime U, where U here is the left side Hamiltonian. So that's the left side Hamiltonian. Run it up to here. Now what's guaranteed is that if A double prime acts at this time, it leaves the same final state as A prime would have left if it had acted over here. Okay? So one might expect that by acting with A double prime, you must send a message to A. A double prime in this context is like R sub B. It's a thing which at equal times here is entangled with B and which is representing the message A. Okay, so that's A double prime. And tampering with A double prime, one might expect, is the same thing as at a later time is the same as tampering with A. Sorry, tampering with, you know what I mean. Okay, so how on earth can it be that tampering with something in the field theory up at this time here can send a signal to A? And the answer is, when you run an operator from here to here, it gets exceedingly complicated. It becomes what Joe and I and Nick Tumbas called precursors. Exceedingly complicated, monstrous Wilson loops and who knows what, which are very, very non-local. So on this time slice here, they're extremely non-local in the field theory, and that means they must penetrate deep into the interior. So this operator here, to the extent that you in any sense that you can identify it with the bulk, is somewheres in here. Sufficiently complicated and sufficiently spread out that yes, it can send a message to A. And I think this has to be. I don't think we have any choice. Every operation I did here was an operation, well-defined operation in the CFD. And if you can send a message from A prime to here, then this also must be able to send a message. Okay, now let's ask, what about the analog? That's the analog of RB. What's the analog of these easy messages? Or the easy things that we don't expect to send a message here? Well, I would just say they're the single trace local operators at the boundary. Yeah.
Why is that the analogy? I remind you that one of the things we showed is that even ordering one
Good.
Can you explain more why that's the analogy? Because one of the things we showed is that E has an order 1 commutator with A prime. So is that true also of what your analogy for
Good.
E?
Excellent. Excellent. Do you want me to answer that or to go on? No, I'm serious. Well, this is a really interesting question.
You decide when, but this is the question that I wondered about for quite a while.
Would you please bring it up again? Good. And I do know the answer, but let's. Okay, so what is A double prime? A double prime is, easy operators, I think, of as single trace operators near the boundary. Okay, let's accept that for a moment. And let's also accept that when they act, they do not send signals to A. We know what they do. They're at the boundary. They send signals up here. Okay? We know what they do.
What's the analog of an operator where I measure the entire Hawking radiation and it's more than half? and I want to have the self-adjustment going on. What would that look like over here? Can that be?
Let's say A double prime is measuring more than as.
Yeah, I measured the whole Hawking radiation, so not just one little particle.
I'm not sure. I don't know. I didn't think about it. I don't know. I don't know. What's the answer to that one?
I think there isn't any.
Yeah.
There are some measurements.
Right, but I mean, I don't think that, for example, your argument about all the states that can be generated by using different slices of the Hartle-Hawking state generates enough states to accommodate that. So I don't think that there's a representation of that in terms of the eternal.
I don't know.
The vacuum eternal black hole.
It's not this geometry. It's something that is this geometry before you made the measurement.
Yeah.
And then after you make the measurement, it's replaced by something else.
Right. I think it's no longer true that A double prime. So in the case of A double prime, then you could argue that when he evolves it back, it gets very diffused by the time he gets down to A prime. I don't think that will be true anymore.
Again, I'm very close to the end. So let's and then we can get to this discussion. All right. The point is that in a sense that I'll spell out in a moment, A double prime, even though it's extremely non-local, maybe made out of giant Wilson loops and so forth, is nevertheless a function of the local operators. And the way to see that is just to say we know what it is. It's U, A prime, U. U is a local bound. A prime is a local boundary. This thing here is just e to the minus I h t, where h is the left side Hamiltonian. This one is e to the plus I h t. And H is just the boundary Hamiltonian. It is a simple operator, a single trace local operator, the Hamiltonian density. So when you expand this out, you've made A double prime out of all these operators. So you have a very similar paradox going on here. Any finite number or any small number of these easy operators can't send a message here, but somehow this thing can. I think what's going on, as Don pointed out, is when you start expanding this in commutators and so forth, you start generating incrementally delta functions, derivatives of delta functions, double derivatives of delta functions, and so forth. And when you add up enough of them, you can send a message to A. I believe that's what's going on. There is a very deep paradox associated with all of this. I won't have time to talk about it unless it comes up in the discussion. But that's kind of the.
Sorry, but I think we did answer Joe's question. I think we did.
Which one was it? Do you remember?
Well, I guess this.
No.
This is the end of your talk.
Yeah. Is now time to answer that question?
Whenever you're ready.
Don't worry about it. I thought you
No, I did not answer it.
Fine.
No, I put it off. And I was, let me answer it. Okay. So, is A prime really A? No. And the reason is, in lowest order, let's say large N limit, let's start with large N limit, there's a geometry here. The geometry is the black hole geometry. A signal from here can scatter off the black hole geometry and go here. That's the origin of in a leading approximation of the commutator between A prime and A double prime. Or sorry, between A prime and E. Well, how do commutators have to do with signals? Let me give you. Let me.
Remember, part of the problem is your analysis. So, in terms of Hawking radiation, E is a simple measurement on one bit.
That's right.
In this analogy, E is pretty much a random operator chosen from the Hilbert space on the left side. It doesn't have. There's no reason to think it has a simple geometric realization because we know it has an order 1 commutator with pretty much everything else. So I don't.
This thing will have an order 1 commutator with. I'm now questioning whether A double prime or A prime are equal to A literally as operators. Literally as operators. And the answer is definitely not. So let me show you why. Even though you can send the signal from here to here, they cannot be the same as operators. So there's a geometry here, and there's a geometry here, and so forth. Signals can get scattered and scattered that direction.
This is gray body factors?
Yeah.
Is that, I mean, that's the issue? I mean, so that, you think that's the issue, gray body factors?
That's only a part of it. That's a small part of it. All right, so from here immediately, yeah, I know, the gray body factors are not going to be very interesting in this, but I'll just tell you, let me make my statement. All right, so signal can get scattered from here to here. You might think that that means that A is A prime except degraded by a transmission factor. But not so. Just as a signal can get scattered from here to here, a signal can get scattered from here up to here. All right? So A has in it other stuff. In fact, you can rearrange it so that A has in it E. You can do a trick to rewrite it so that A has A prime and E. But it has more than that. It has stuff from this side. A signal from here can get scattered to here. Even worse, a signal from here can collide with a signal from here and make a mess that affects A. So it's simply not true that in an operator sense, A is equal to A prime. If you take, there are simple examples, just a field theory in 1 + 1 dimension, free massless field theory with Dirichlet boundary conditions. Take A prime over here and set it equal to d phi by dz. dx. Okay. Take A up here and write it and think of it as d phi by dx minus. Okay? Free massless scalar field theory, d phi by dx is equal to d phi by dx minus over here. Okay? Now you might go up to here. Let's call this point A double prime and set it equal to d phi by dx again. It's just another operator up here. All right, you say that this doesn't commute with this. But this is equal to this. How can it not commute with this? Well, the answer is very simple. In fact, in free massless field theory, this does commute with this. The commutator is on the light cone. But now supposing I put some scatterer in here, for example, a mass term in here. Then you find that waves scatter off here and make a commutator. So in the same approximation that A is equal to A prime, the commutator is 0. When you start correcting it perturbatively or otherwise, at the same time that you start finding a commutator, you start finding corrections to A equals A prime. So, but in the end of the day, what's up here will commute with what's over here. And I don't think I have to prove that. When you've done all the corrections and figured out exactly what the relationship is between A and various other operators over here, this will commute with this. Okay. Now that's all I understand, except for a paradox which I don't understand, which I won't have time for.
Okay, I do think I think you're still working with a very non-generic E, whereas our point was that effectively the butterfly effect made RE a very generic thing. But this is something to think about offline.
Okay.
I'd also like to emphasize that, as I understand it, the reflection event you talk about, which gives a non-zero commutator between A prime and E,
yes,
is not scattering off a classical black hole. It's absorption by the black hole and re-emission as Hawking radiation. It's related to what you call the scrambling process.
At the moment, I'm just solving the wave equation.
I understand.
Right.
But
no, well taken, but yeah. But you can see this in just a simple field theory with a scatterer that you have to do a complicated perturbative, or it doesn't have to be perturbative, but let's say a complicated perturbation theory. And I would guess that you could probably figure out what A prime is in terms of boundary operators. Sorry, what A is in terms of boundary operators perturbatively in orders of 1 over n, or in terms of gravitational perturbation theory.
But of course, as you say, your simple model won't have an A double prime that fails to commute. That's because it doesn't have a scrambling type process.
Yeah. No, this is just an illustration that. There. Yes, Douglas.
Yeah, since you're sort of suggesting a technical problem with this commutator argument, I feel sort of compelled to respond
that what you've constructed here is
Juan, stand in front of me.
You've constructed
my advisor will stand in front of me while my student attacks me. Go ahead.
You've constructed a particular operator E. So you argue that commutes with A.
Yeah.
Okay, and you've given an argument that should be true. But what we're really interested in with the commutator argument is the case with Hawking radiation. Yeah. And there it can't, if A is equal to any operator in the Hawking radiation, then it can't commute with all local operators.
It looks the same to me. I think it's the same, isn't it? You see the difference? Well, we have to think about it. I don't see the difference.
There's just no operator on the Hawking radiation that commutes with all of the simple operators.
But this operator is not just made out of the left-hand side. It's a complicated construction involving operators at different times, operators from this side. Okay, I don't have a complete answer, but one way I like to think about it, a sort of naive intuition, is that the A double prime type operators are sufficiently non-local that they reach way, way into the interior of the bridge. They reach way, way deep into the interior of the bridge, whereas the simple operators never reach deep into the interior of the bridge. And I would like to believe, again, this is a hope, that we can understand some way in which the very complicated manipulation of R sub B here reaches very deep into the bridge, and the simple operations here don't. But I can't, the best I can do is just to illustrate it here for A double prime, how it reaches into the bridge, even though the individual contributions to it are simple operators. So, yeah.
Lenny, can you say a little bit more about what would happen, again, for a very large measurement of all the radiation, how that connects with...
I never thought...
because it seems to me that the definition of this picture is that the left CFT is the purification of the zone.
Absolutely.
And then you get the vacuum, but then you also get this problem.
There are many approximate purifications of the zone. In the same sense that there are many decompositions of the Hawking radiation.
That's true as long as you don't measure too many bits. That's why I'm saying let's consider the case where you measure the entire Hawking radiation and it's more than half of the system. And then I think you get into the same difficulty that the only way to define what is by the left side.
Okay, what is the difficulty?
I think the only definition that you've given that I understand what this left side represents is the purification of B, whatever that may be. And if that's the definition, then of course you can't excite the vacuum near the horizon, and you again have a violation of the equivalence principle. Because then the apparatus that was supposed to excite
in this particular case, incidentally, in this particular case with equal entropy on both sides, I don't really think it is true that the left-hand side is a purification. It doesn't have enough, has the same number of qubits as the right-hand side. So I think, I think you really have to include stuff from the right-hand side too. In other words, I think you really have to write.
But that's I'm granting you that.
Yeah. Okay.
So that's why I'm assuming it has to be more than half. The radiation has to be more than half. That's enough to destroy the message.
Wait. Let me just ask you, are you saying that measuring more than half creates a firewall? I think I would agree with that. Or creates a bad disturbance.
You're okay with saying that if I have a black hole in a galaxy and it's more than half.
You're not talking about making one of these very difficult measurements. You're talking just.
Yeah.
Oh, I don't. I think it just. No, I don't think it does anything. I think it just rearranges the code.
Exactly, and the code. So then you're saying that you're representing the purification of B in your picture as the left CFT. Whatever may have happened to the radiation, if it ran into the CMB, it's also still the vacuum, right? Right. So in that case, unless you can give some alternative definition of what the left side represents, I think you will always have the vacuum at the horizon, because then if you interact with B when you fall in, and you think you would be exciting B, that's really just spreading the purification around even more.
I think I was trying to explain why complicated measurements like RB do disturb the interior.
Maybe they do.
Yeah.
What I'm saying is that even for simple measurements, I don't think the only definition that I understand of what this left side represents is the full purification of B, and then that will lead to overkill.
Why? Do you understand? Sometimes I draw blanks when people explain things to me, but...
Well, in this example, we have, there is the black hole, and you can modify it, right? So there are different bridges for different states. So you can add a particle, or you can do various things, right? Mm-hmm. So what is needed is that somehow the upper corner is somewhat reasonable, right? We can...
I guess what I'm questioning is whether this example can represent a one-sided black hole in which the Hawking radiation is interacted with a very large environment.
Well, I think the answer is no. This example is a very special set of two states, and well, the correct example will be more like this other thing, this octopus that Lenny.
Right. Yeah.
And we don't know what the properties of that thing really are. So all that one needs to have a smooth horizon is that near the upper corner is close to the vacuum.
Going back to the very beginning of your talk, I'm still just really confused about something, which is that if there's no linear operator that tells you whether there's a firewall or not, then how scary could the firewall possibly be?
Well, I don't think there are firewalls, but apart from that. Okay, so the question, let me phrase it differently. I think it's the same question. But am I doing something really bad by violating linearity or whatever?
No. I'm just trying, like entanglement. I know that there's no linear operator that tells you if your state. So fine. So to detect entanglement, you have to know which specific entangled state, right? But it would be odd to say that to detect whether someone died or not, you have to know the specific way that they died. And
exactly.
Yeah.
Exactly.
Okay.
Exactly. The whole logic of observables and measurement and so forth goes something like this. You do a measurement on a system, you record the measurement in some system, the record is a public record that other people can look at and so forth, and when you put all that stuff together, you find out that measurements have to correspond to linear subspaces.
Right.
Okay. There is no analog for detecting a firewall. A firewall detecting a firewall, you don't detect a firewall. In the sense that you don't produce a public record that other people can look at. So it's not at all clear to me that the logic of operational quantum mechanics should apply to this. Now, I think what you do have to be able to show is that this kind of hypothesis doesn't infect and I don't think we're anywhere. I certainly haven't done this. Doesn't infect or affect the linearity of the quantum mechanics of any given observer. Well, yeah, I know you do, but we can try to sort that out. But I would be upset if it led to operational violations of quantum mechanics for an infalling observer in a laboratory, a closed laboratory. You jump in, surrounded by a closed laboratory, you do measurements on your spins or whatever I would be quite upset if this led to, I would say it's a nonlinearity or state dependence or whatever you want to call it, of the mapping or of the coding of the exterior degrees of freedom with the interior. But it's not necessarily a violation of the quantum mechanics of either the person outside or inside. It's a non-linearity or state dependence in the translation between them. But I think it remains to be seen whether this is viable in the sense that it doesn't lead to bad things for the infalling observer. So, I don't know. Does that satisfy you?
I mean, so your part of your answer was supposing that there is an inside observer. Right?
Yeah.
Which in saying that, well, the solution is that there's no public records, so we don't need a linear operator. I mean, it sort of makes you wonder whether whether your answer is just tantamount to saying that we're no longer doing physics to ask such a question, right?
You have a really big black hole.
Yeah.
The black hole is big enough that when you jump into it, you will survive for much more than your own lifetime. You can do experiments when you fall in and so forth. do we count that as doing physics or not? And I get very confused when I think about it.
Okay.
Right.
All right.
You're right. Okay, thank you.
We reconvene at 2.